you very much to Ali and to FESI for the kind invitation to deliver a plenary talk. So my name is Emilio Martinez-Paneda. I'm an academic at the University of Oxford, where I lead the Mechanics and Materials Lab. And today I want to tell you about what we have been doing in the area of hydrogen embrittlement, how we're trying to develop mechanistic, physically based models that can reliably tell us when hydrogen-assisted fractures will take place. And the motivation for this work is clear. Hydrogen is going to play a key role in the energy transition because it has the potential to decarbonize many applications and sectors, including some that are known to be particularly difficult to decarbonize, such as aviation or steelmaking. And the jury is still out on how much we will decarbonize using hydrogen versus electrification, but it's clear that there's no alternative to hydrogen to decarbonize fertilizers, maritime transport, aviation, some steelmaking processes. So it's clear that we will need hydrogen. How much? Still to be decided, but we will for sure need it. And as you can see here in this Royal Society report, hydrogen is also deemed to be the best solution for large-scale electricity storage. And of course, large-scale electricity storage is fundamental to a society based on high renewable energy. So yes, hydrogen is going to be there, and governments around the world are investing significant amounts of money in establishing a hydrogen energy infrastructure that currently doesn't exist to store and transport this green hydrogen. You see in the slide what is Europe's hydrogen backbone, which is a framework of 40,000 kilometers pipelines that includes some new pipes, but mostly, as you can see with the dark color, mostly natural gas pipelines that are being retrofitted or repurposed to transport hydrogen gas. And as you can see from this newspaper article, some countries are already starting to do so. Germany has already hundreds of kilometers of hydrogen transport pipelines, and the UK is also planning to do so very soon. But the problem with hydrogen is that it has a dark side. We know since almost 150 years ago, the hydrogen makes metals brittle. And you can see this in this paper from Johnson in the Proceedings of the Royal Society, where he talks about some remarkable and extraordinary decrease in toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, scientific writing used to be very objective. You will rarely see words such as remarkable or extraordinary. But the way that hydrogen interacts with metals is indeed quite remarkable and extraordinary. You can see some examples here. So on the left, I'm showing some uniaxial stress strain curves. And you see that if I introduce hydrogen into my samples, for example, by exposing them to hydrogen gas, then you can see that there's a very significant reduction in ductility in failure strain. This is a pipeline steel, by the way. In the middle, you see the impact on toughness. That is quite remarkable. You see this is for a pressure vessel steel, that just 6 parts per million of hydrogen, so a tiny amount of hydrogen, takes you all the way from this 220 megapascal square root meter fracture toughness to below 20 megapascal square root meter. So a tiny amount of hydrogen makes my pressure vessel steel go from reduce an order of magnitude the fracture resistance of my pressure vessel steel, going from something very ductile to something that is as brittle as an engineering ceramic. And then the effect is also quite significant on fatigue crack growth. You see this here. These are for pipeline steels exposed to hydrogen gas. This is the log-log plot. This is the response in air. And this is over the Paris law regime, the response in hydrogen. You can see that there's at least 1 order of magnitude elevation in fatigue crack growth rates. So we may wonder how we're going to be able to deploy this hydrogen storage and transport infrastructure, given that the materials that we use for storage and transport become so susceptible to this hydrogen embrittlement phenomenon. And hydrogen embrittlement is an old foe. It has been with us for quite a while now. It is typically associated or traditionally has been associated with very aggressive environments where you have a lot of hydrogen. This is the case of this oil and gas failure. In fact, this is the biggest environmental disaster in the history of humankind, the Thunder Horse accident, which was due to a hydrogen embrittlement problem. You generate a lot of hydrogen in these H2S environments. But not only in this environment, so with the use of modern high-strength steels, which are more susceptible to hydrogen, we are seeing hydrogen-assisted failures in many applications and sectors, just because of the hydrogen coming from the humidity or from the manufacturing processes. You see here a couple of famous examples, the San Francisco Bay Bridge bolt failure, but also the cheese grater or Leadenhall Tower in London, one of the most famous skyscrapers in London from a few years ago. And of course, this is going to be an even bigger problem when it comes to thinking of this energy transition, where we want to store and transport hydrogen gas at large scale. And even though, the technology is not even there, very few countries have already started to deploy in this infrastructure. Those very few countries are already starting to see accidents as a result of those hydrogen-assisted fractures. So basically what we need is some sort of mechanistic tool and mechanistic framework that allows us to predict when these things will happen and therefore prevent them from happening, but also to map what are safe regimes of operation to be able to accelerate this energy transition, to be able to more fast and safely deploy this hydrogen energy infrastructure. So this is what we've been working on in my group for the past few years, trying to develop a mechanistic computational model capable of predicting when hydrogen-assisted failures will happen. And my philosophy here has always been to maximize the physics, to minimize assumptions and parameters. At the end of the day, ideally, I would like to have a model that does not rely on any magic fitting parameters, alpha, beta, that have no physical meaning. I would like to have a model that relies purely on well-identified physical properties that I can independently measure in my lab. Yield stress, diffusivity, things that have a clear physical meaning. And in order to do that, the only way you can do it is by trying to resolve the physics of your problem explicitly, directly. So I'll explain how our modeling framework encompasses the three main stages of hydrogen embrittlement: the hydrogen ingress part, so the uptake of hydrogen to the metal, the transport of hydrogen within the component, within the material, and finally the embrittlement process itself, how hydrogen assists in nucleating and growing cracks. So let me go one by one. We start with the uptake stage. And here the goal is, for a given environment, predict what is the hydrogen concentration at the surface of my metal. And hydrogen can come from many places, from gaseous hydrogen, for any environment that contains hydrogen molecules, aqueous electrolytes, from manufacturing processes, welding, from soil. But the two main environments I'm going to focus today is gaseous environments, which is relevant to the energy transition. We store and transport hydrogen in gaseous form, typically. And also aqueous electrolytes, relevant, for example, to that oil and gas failure that I showed you before. And the good news is that for a gaseous environment, under steady state conditions, we do have a closed form solution. So this is what we call Siebert's law, and relates the quantity that I'm interested in, the hydrogen concentration at the surface, with the quantity described in the environment, right? The hydrogen pressure. This is something that I know or I define as an engineer. And the only thing that connects them is this material solubility that I can identify easily with a permeation test. And the one thing one has to be careful here is that this material solubility depends on the hydrostatic stress. You can show this very easily here, and you see that this blue term here has an exponential term with a hydrostatic stress inside of it. So the coupling with mechanics is very strong, and normally we measure the stress-free solubility in a permeation test. So one has to be careful and be aware that that stress-free solubility has to be enhanced with your mechanics if you want to accurately predict what is the concentration of hydrogen ahead of stress concentrators such as cracks. But again, this is good news because, well, I can measure the stress-free solubility. This term comes from a finite element analysis for whatever defect I have. This comes from the environment, so I can predict my hydrogen concentration. In the case of an aqueous electrolyte, problems are much more complicated. So you not only need to resolve the surface reactions happening at the interface between the metal and the electrolyte, but you also need to resolve the electrochemistry of the electrolyte, which we know can be very different inside of cracks and occluded electrochemistries to the bulk, where you can do your engineering measurements. The good news is that we know what are the differential equations, the mathematical equations that describe each of these phenomena. So in the surface, we have the Bolmer, Hurwitz, Tafel, and absorption reactions. So you need to resolve those hydrogen revolution and absorption reactions. Again, we know the maths for that. And in the electrolyte, you solve for the electrochemistry, so Nernst-Planck and the electroneutrality condition, which again are relatively well established and are the type of models and equations that we like, right? Because how those ionic concentrations change depends on diffusivity, on Faraday's constant, temperature, gas constant, things that we have a clear physical meaning that we can independently measure. And when you do that, well, you solve these equations in your favorite finite element framework. And this is the type of boundary value problem that you solve, where you have an electrolyte with many ionic species, and then a metal that is deforming and has hydrogen being ingressed into it. And every of these variables is a nodal degree of freedom. So as you can see, the models can get a bit heavy, but computers are big enough these days that we can tackle those problems. And then the representative result that you get will be something like this, where I'm plotting on the electrolyte any relevant quantity, in this case the pH. You can see how it varies quite dramatically inside of the crack to the place where we do our measurements, hence why we need these modeling tools. And then you can see that for any choice of environment, material, loading condition, I can predict time, I can predict what is the hydrogen uptake and distribution within my sample. And these models have proven quite useful. We published this a few years ago for three main reasons. One is that it allows us to predict hydrogen embrittlement in aqueous electrolyte environment. So I have, for example, relevant to that oil and gas failure that I showed you before, for a given environment, I can predict what is the uptake of hydrogen, and then I can predict how much hydrogen changes our mechanical and fracture properties. The other reason why they have become quite popular is that they become very useful for the electrocatalysis community. So apparently they didn't have a good model, but they're very interested in optimizing the hydrogen revolution reactions and developing electrolyzers that optimize that behavior. So this model has proven to be quite useful for them. And then finally, last but certainly not least, you can use these models to establish a correlation between aqueous electrolytes and gaseous environments. And this is important because gaseous environments are what matters when it comes to the energy transition. However, doing experiments in gaseous environments is not only expensive, but also difficult and challenging from a health and safety point of view. So we can introduce the hydrogen to our samples using an aqueous electrolyte, which is much cheaper and easier. And then we can quantify for that hydrogen, for that aqueous electrolyte, what is the equivalent hydrogen concentration. So if I go to my crack tip, I can input this here and then understand what is the equivalent hydrogen pressure. So we can establish a correlation between electrochemical and gaseous environments. Okay, once you know how much hydrogen you have in the surface of your metal, you want to figure out how is that hydrogen distributed within your material, your microstructure, or your component. This is also relatively well understood. Hydrogen moves around. So this is the variation of hydrogen concentration with time as a function of gradients of concentration and gradients of hydrostatic stress. Again, the coupling with mechanics is very strong. You can see here, this is the steady state solution for this equation. You can see that the hydrogen concentration has this exponential term where again, the hydrostatic stress is inside of that exponential term. So the hydrogen content ahead of a crack is going to be much, much higher than elsewhere. And basically, you can implement that equation into your favorite finite element package. And when you do that, then you can simulate any boundary value problem and see how the hydrogen distributes. For example, here, this is a pipeline with a weld. You see how the hydrogen diffuses through the pipeline. This is a pressure vessel, microstructure, any geometry that you're interested in, you're able to predict the distribution of hydrogen in time and space. But this is only part of the picture. Hydrogen not only travels freely through the crystal lattice, it's also sequestered at what we call hydrogen traps, so microstructural defects, grain boundaries, carbides, dislocations. And we can easily extend the model that I showed you before. You can see here, this is very similar to what we had before. The only difference is that now we have an effective diffusivity that basically characterizes the fact that as the hydrogen encounters those traps, it slows down its lattice diffusivity. So basically, the model relies on two parameters. So you now have a lattice hydrogen concentration and a trap hydrogen concentration. And predictions rely on two extra variables or physical properties. The trap density, how many traps you have. This is relatively easy. You figure out how many grains you have for a given volume. And the trap binding energy. This tells you how energetically favorable it is for a hydrogen atom to go to a grain boundary or a dislocation or a carbide. And this is something that we can measure using TDS, thermal desorption spectroscopy. And we have developed something that we have in our lab. And we also develop something called the TDS simulator, which is a Python and MATLAB app that allows you to easily identify these binding energies and trap densities from these TDS measurements. One thing I will say about these traps is that there's again a coupling with mechanics, because in general, the trap density doesn't really change. The number of grain boundaries that you have doesn't change with mechanical straining typically. However, dislocation traps will change. The number of dislocations that you have, of course, is related to dislocation density, which is related itself to plastic strains, but also to plastic strain gradients. And this is an important bit. GNDs dominate behavior near inclusions, cracks, and other stress concentrators. And GNDs are also obstacles to other dislocations, so they bring local hardening, as you can capture through strain gradient plasticity theories. And when you do that, it's the only way that you can actually show that you are able to capture the very high hydrogen concentrations that you see ahead of cracks and other stress concentrators, like you see here in the experiments. So GNDs strain gradients are important. Then once you know how much hydrogen you have, where and when, then you need to predict the fracture. How does hydrogen interact with cracks? And here there are two challenges. One physical, how does hydrogen actually embrittle metals? And the other one is computational. So you need to be able to have a tool that allows you to simulate how cracks evolve. Cracks are discontinuities, interfaces. We don't like discontinuities. We like things to be smooth. And in order, we need to be able to capture how this discontinuity evolves, combined with all the chemomechanics or electrochemomechanics that I showed you before, like moving boundary conditions and so on. So that's a challenge. And what has worked very well for us there is phase field models. Phase field models have been a revolution in many areas of science and engineering. The idea is that you replace a discontinuous sharp interface by an implicit domain, an implicit interface. You use the auxiliary variable to smear that interface over a finite domain, and then you solve implicitly for the evolution of this phase field variable. And this phase field variable tells you basically whether you are inside of the crack or outside of the crack. I mean, this has been going on for quite a while. It was first proposed in the context of microstructural evolution, solidification, what is now by far the most dominant technique. It also very quickly has become the most powerful or popular technique to simulate cracking and fracture mechanics problems. You can see here why. This is the output of a simulation, hydraulic fracture problem, hence what you see these complicated cracking patterns. And you can see that you see crack branching, nucleation of secondary cracks, coalescence of multiple cracks, very complicated cracking phenomena that we can only model basically thanks to these tools. There's no other way we could simulate such a complicated cracking phenomena. And I won't have time to discuss corrosion, but we have shown quite recently in my group, but also in a group in Hong Kong and another one in the US, that you can use the same idea, the phase field, to simulate the evolution of the corrosion front, to capture material dissolution and corrosion. And this is quite important because corrosion is a long-standing and complicated and important problem, but this provides an avenue for us to simulate this corrosion process and therefore predict corrosion failure. So it's a very new field, but it's growing fast, and I think this is an area where I'll recommend early career researchers and academics to work, because I think it's going to be, it's going to be very popular in a few years' time. It's already becoming very popular very far. But today I'm going to focus all about fracture. I want to predict the evolution of cracks together with all my hydrogen environment. And the good thing is that phase field not only is a powerful computational technique in the sense that it allows you to simulate very complicated cracking patterns without convergence issues and on the origin of an element mesh, but it's also physically sound, because it's based on basically on Griffith's energy balance, on the thermodynamics of fracture. So it's effectively a competition between the strain energy density, the energy that you store in your material, and the fracture toughness. The toughness, something, again, a material property that I can easily measure. And this is the phase field evolution equation that dictates the value of this phase field. That's kind of like a damage variable. You see it goes from 0 in intermaterial points to red 1 in cracks, inside of cracks. This is, by the way, a crack branching due to the application of a dynamic load as predicted by phase field. And then, like a damage variable, it basically degrades your load carrying capacity. And here you see some examples of how phase field has been used to across many applications and sectors. So these are examples from my group, but also from the literature. You see examples in metals, ceramics, composites, functional graded materials. And in all of them, you can see that not only we are able to capture very complicated cracking patterns, but we're able to do so showing a remarkable agreement with experiments. So it's physically sound and computationally very powerful. But nothing had been done on hydrogen, so we proposed the first phase field model for hydrogen embrittlement. And for that, we proposed a series of models, but the simplest one you can think of is one where you solve for the deformation, diffusion, and damage process. And I'm highlighting here some of the couplings, but of course the key coupling is this one. How does hydrogen reduce your fracture energy, your fracture toughness? And we know qualitatively what happens. The more hydrogen you have, the less fracture resistance. But the key question is how you do that quantitatively. And we've done it in two ways. One is what I call the mechanistic approach, where we basically try to understand how this happens. So we look at the atomistics, we look at the DFT, and we are able to predict how, as a function of hydrogen occupancy on a relevant interface, like a grain boundary, we can atomistically, from first principles, predict what is degradation in fracture energy. And then based on this DFT calculation that we do once in our lifetime offline, we can directly input that into our model. But, working with industry, a lot of industry partners tell us as well, we don't really trust atomistics that much. And never, in any case, we have a lot of data of fracture energy versus hydrogen concentration. So why don't we just feed that data and incorporate that into our model? And this is something you can do, of course. And we've been using these models for quite some time now, and we've been able to show that they are able to capture very well experiments. You see an example here. Symbols are experimental data points. You see examples here with high-strength steels, duplex stainless steels, pipeline materials. These are arc cures without hydrogen, with hydrogen. These are experiments on duplex stainless steels. And you can see that we got very good agreement, but not only we're able to reproduce, lab or academic experiments, we're also able to handle the complexity and the large scales involved in engineering practice, which means that you can bring this idea of virtual testing to the hydrogen energy sector. And so let me just finish over the last 5 to 7 minutes telling you or providing 2 case studies that I hope highlight the potential of these methods. The first one is related to predicting hydrogen-assisted fatigue. So, of course, as you can imagine, most of the components in the hydrogen energy sector are going to be exposed not only to hydrogen, but also to cyclic loading. So we need to be able to predict what is the effect of hydrogen fatigue. And some data is out there. So this is, for example, data from Sandia National Labs, where you see fatigue crack growth rate for different hydrogen pressures, up to 100 megapascals for hydrogen pressure, different load ratios, and different frequencies. And this data is very, very useful, but it has some limitations. And by the way, as you say, very few labs in the world are able to obtain this data. 100 megapascal hydrogen pressure is very difficult to deal with. I would say a handful of labs in the world can capture this type of data. So the data is scarce and very useful, but it has some limitations. One is that practical applications involve low loading frequencies, and there's a frequency effect here. When you load, if you load very slowly, then there's more time for the hydrogen to accumulate, and therefore when we do fast experiments, we're being non-conservative. So ideally, we like to do experiments very slow. We can't, so there's a problem here. The data is non-conservative. The data is also tied to the test conditions. So each of these points is useful for one frequency, one load ratio, one material, one hydrogen pressure. But of course, we want to be able to consider other conditions. And also, this is, of course, by the way, for a given load ratio, but realistic loading histories are much more complicated than that, and we cannot apply superposition since hydrogen brings a history dependency, and we will also like to predict the nucleation of cracks. So we try to model this, and the way you do that is basically you add a fatigue degradation function that has a variable that accumulates with your cyclic history and degrades your fracture toughness. And this fatigue degradation function has 2 parameters that basically characterize how susceptible your material is to cyclic loading. And this area of facile fatigue is a growing area. It's again, very new, but growing fast. But it's still an area that is much less mature than any of the other things that I discussed so far. Meaning that these 2 parameters, while they have a clear physical meaning, susceptibility to cyclic loading, they're not yet so well understood. So we need to fit them, basically. But that's no problem. So we did this in collaboration with Tenaris. They have some data for in air. So they said, okay, we know that this N and alpha you need to calibrate. So we give you this data in air. Run your experiment. So here we run our virtual experiment. You see the crack growing, and then of course we get a perfect agreement because we are calibrating that alpha and N. Those are material properties that we calibrate. But now all the calibration is done because all the other things are material properties. So now the question is, okay, can you blindly predict data? So this is data that they had at 55 megapascal hydrogen pressure. So we're not allowed to touch anything in the model, not to change any of the parameters. We apply a boundary condition from the Siebert's law. We know for this pressure what is the corresponding hydrogen concentration. We put it into the model, and the line was the prediction of the model. So that was good. They also had data for a different pressure, 106 megapascals. So again, not touching anything in the model. All the parameters remain the same. We just changed the amount of hydrogen that we have. That came over the model, so a very good agreement as well. We were quite happy. They also have data for different load ratios. So again, we don't touch anything in the model. The only thing we do is we change the way we load our sample. And this came out of the model. So again, we were quite happy and impressed. They also have data for different load ratios with different pressures. Again, not touching anything, just changing the way we load our sample. A very good agreement all over the board. They have data for different loading frequencies. We just load slower, faster. That's what came out of the model. And this is for a given load ratio. They have data for a different frequency, different load ratio. Again, a decent agreement, I would argue. So all the data that we threw to the model was able to blindly predict without any recalibration whatsoever. So I think that's quite powerful. And we recently used this to predict the behavior of full-scale components. So this is a pressure vessel. And you can see here how the crack is growing, the pressure vessel. They had done full-scale experiments for pressure vessels with 2 different materials and notch configurations. And you can see the number of cycles to failure of our 3D simulations agrees quite well with the experiment. And the last case study is related to hydrogen transport pipelines. I said before, we want to deploy over the next 4 years, 40,000 kilometers of hydrogen pipelines. The Germans already have a few hundred. But this is a problem because, as you can see here, the toughness of pipeline steels reduces quite significantly with hydrogen. And these natural gas pipelines have been there for a long time. So we need to understand under what conditions can hydrogen be safely transported in the existing natural gas pipelines. And this is a very difficult question to answer with experiments for a number of reasons. One is that we have a quasi-infinite combination of pipe and well materials. So we've been developing these natural gas pipelines, deploying them for 5-6 decades now. So we have different modern and vintage materials. We did welding in different conditions. We have a wide range of pre-existing defects. And also as an engineer, you have a quasi-infinite combination of parameters that you can decide. You can transport hydrogen, pure hydrogen that is blended 5% with natural gas. You can also transport hydrogen at 100 bar, at 10 bar, at 5 bars. It's completely up to you. So there's many, many combinations, too many to test experimentally. The other problem is that what is going to fail first are the wells. They're the weakest link in the pipeline. Mostly the heat-affected zone, right? This area where things become brittle and hard. But, the heat-affected zone is very small, so we cannot really extract compotential samples to do fracture experiments there. And even when you do full-scale experiments, it's a bit difficult because you have a native oxide layer that might prevent hydrogen uptake over the duration of your full-scale experiment, but not over the duration of the of these decades that we want to transport hydrogen in pipes. So we need models. And what we did was to set up a new framework where we combine those deformation, diffusion, fracture, phase yield models that I showed you before with welding process modeling. And there's an entire community, I saw a few talks in this conference dedicated to either additive manufacturing or welding process modeling. So we basically took off the shelf some of the models, but I was quite impressed by the quality of those models. And basically you run thermometallurgical simulations that tell you, what is the residual stress, what is the state, what is the distribution of properties in the material. That allows you to get hardness maps that you can compare to experiments, and then you run your couple deformation diffusion model. So let me show you an example. This is a welding process. So on the top is a seam weld. On the bottom is a girth weld. You see how we simulate the different passes, and then you predict not only the temperature distribution, residual stresses, but also how the different, depending on your cooling rates, what is your phase fraction, right? Ferrite, perlite, bainite, austenite, how this changes. And these models are relatively empirical, but they're actually quite good. I was quite impressed by them. You can see that, depending on your phase fraction, what is the hardness of your material. So that allows you to validate. So you see here 2 types of welds. We apply the same welding protocol. And as you can see, we got actually quite a good agreement when it comes to the hardness maps experiment versus the model. So I was quite impressed with these models. And here you see a comparison with residual stresses. It's difficult to measure residual stresses in experiments. You see here, this is with X-ray diffraction. But again, using the same scale as in the hardness maps, we get what I would say is quite a decent agreement. So then we use this because now we know naturally what is the distribution of properties and therefore the susceptibility to having. We naturally capture the fact that this heat-affected zone is going to be more susceptible. So we basically now ramp up the pressure. You can see here we're ramping up the pressure. We see the hydrogen distributing. And at some point, you will see here that a crack forms. When we reach a critical pressure, the crack will grow and the entire thing will fail. So we did that, and we basically quantify at what pressures things will fail. We also try to learn things. We know that the welding standards allow you to have certain types of defects due to, lack of fusion, group contraction. So we incorporated those defects that are safe in natural gas, but as we realized, they're not always safe when it comes to hydrogen. And then we learn a few things, and some of the things that we learned, for example, was, of course, the defects play a big role. Macrostructure also plays a big role, and residual stress is also important. So just to finish, just on time, I would just say that I think the combination of phase yield and multiphysics modeling allows us to, or chemomechanical, electrochemomechanical modeling allows us to develop a mechanistic framework that allows us to directly simulate the underlying physical processes in hydrogen uptake, diffusion, and embrittlement, and therefore that allows us to eliminate those fitting coefficients and deliver predictions that are based purely on physical properties. The framework is very general. These are at the end continuum finite element models. It's very easy to incorporate this into your model. And you can readily extend this to fatigue, welding, microstructure. You can combine this with crystal plasticity, whatever you want. And I've shown you, hopefully I've convinced you that we can predict not only laboratory experiments, but also full-scale engineering components. So you can do this virtual testing. And I particularly showed 2 case studies that I thought were quite relevant. Is the application of these models to predict fatigue crest growth, to conduct virtual fatigue crest growth experiments for any arbitrary condition, and also to determine what is the maximum admissible pressures that we can handle in hydrogen transport pipelines. That's all. I will just finish by thank you for your patience. Again, apologizing for not being there. I would love to be there with you. But saying that all our codes are openly shared, so you can download them and reproduce all the results that I showed you today. We do a lot of things in our own packages in C++, Phoenix, Julia, MATLAB, but also we work with commercial packages like COMSOL and Abacus. And actually, COMSOL has implemented a lot of what we do now. They have implemented, for example, the hydrogen uptake model. They have phase field now implemented as an inbuilt feature. So a lot of this stuff you can easily do in COMSOL, just clicking a few buttons. So it's quite convenient. And yeah, just to say, of course, thank you also to my sponsors. Thank you so much for your time.